Okay, so last time convection theory we finished almost. Yeah, we discussed this one also. So let's solve a simple problem. So here we have electrical wire in which current is flowing and it is placed inside a room at a temperature of 15 degrees Celsius. So because of this current and voltage, heat is produced in that wire. And because of this heat, the temperature measured at a particular instant is 152 degrees Celsius. The surface of this wire, its temperature is 152. Ambient is at 15 degrees Celsius. So what we need to find out, the amount of current voltage is given disregarding any heat transfer by radiation. So we are not taking into account radiation so far. Determine the convection heat transfer coefficient. Convection heat transfer coefficient, we use that H, we need to calculate. So this is one way to calculate H. This is an experimental setup to calculate H. Because in this case, because it's all by convection, so we know the general heat transfer equation for convection. Yeah, H surface area into delta T surface temperature minus ambient temperature, because now surface temperature is higher than ambient. So now the H we need to calculate. So all other parameters should be given, which are given, right? Area is given. So it's a cylindrical wire. So the area is?
Which area? Surface of the cell.
The area through which heat is transferred. So this is the wire. So which area? Surface area. This is the area from which heat is transferred from the solid to the air. Yes. So the surface area of the cylinder plus this area is also included. But normally in this case, for a long wire of very small diameter, we can neglect these two. But this is the main area of heat transfer. So this is pi dl or 2 pi rl. Diameter is given, so pi dl. H we need to find out. So everything is given. Surface temperature is 152 minus ambient temperature is 15 delta T. No worry about Kelvin. Okay. Q dot convection. So here for the case of electric wire, I can find out how much electrical work is supplied, which is converted into heat. So I into V. That becomes heat in an electric resistance heater. So that will be this one. So we can find out H. So this convective heat transfer coefficient, which we will find out, that will be from this solid cylinder exposed to ambient air, which is natural convection. That is a problem of natural convection. There is no fan or anything attached. So this will be in that range, smaller range. Maybe, yeah, about this, below 50. Okay, so be careful about the unit, centimeter, meter, etc. So H is 34.9 watts per meter square per degree Celsius. All right. Let's move on. This was a very simple question. Now, next mode of heat transfer. which we need to discuss in this first chapter of heat transfer, and that is radiation. Everybody is emitting radiation because something is going on at atomic level. Molecular level, electrons are moving. These are charged particles. Protons are charged particles. Because of the movement of these charged particles, some energy is emitting from materials, and that energy, we call it radiation. Those are electromagnetic waves. So these are the energies which is traveling in space due to electromagnetic waves. We call it radiation. Okay, so these radiation do not need any medium to travel. They can pass through empty medium, right? Like in vacuum. So, and they are traveling at a speed of light, right? And it doesn't decrease or it doesn't change its magnitude even in a vacuum. These radiation, those are occurring not only from solid surfaces, but also liquids and gases, they also emit radiation. So in other words, every body whose temperature is above 0 Kelvin is actually emitting radiation. And here we are particularly interested in thermal radiation. There are many types of radiation, but here we are only talking about thermal radiation. Thermal radiation is that type of radiation which is produced due to the temperature of any body, right? Any body whose temperature is above 0 Kelvin is emitting these electromagnetic waves, which we call as thermal radiation. So this radiation emission from bodies is a volumetric phenomena. The whole volume of a body is actually emitting radiation, right? Like solids, liquid, gases, they all emit. Not only emit radiation, they are also exposed to radiation. So they may be absorbing some of it, which is falling on them. And then they may be transmitting, absorbing, or reflecting. There are so many phenomena which are involved in the radiation transfer from one body to another. So here we are saying radiation is a volumetric phenomena, but for opaque solids, opaque solid, this is an opaque solid. Whatever radiation will fall on it, it will be either absorbed or reflected. Nothing will be transmitted. So for opaque solids, this is not a volumetric phenomena, this is surface phenomena. Radiation is emitted or absorbed only on the outer surface of those bodies which are opaque, right? So for opaque solids like wood, metal, rocks, which do not transmit radiation, radiation is occurring only on the surface. On very small thickness on the surface is involved in radiation exchange with the other bodies. Whatever radiation is produced within the body, it doesn't reach the surface, right? So for opaque solids, it's a surface phenomena, but not transparent solids like this glass. It's a volumetric phenomena because this glass is not only emitting radiation, it is also absorbing, it is also reflecting, and it is also transmitting radiation. So for
the radiation occurs in the space, right?
Yeah, space, but there is a source. What is the source in the space? For example, in our space, sun is the source, and here is the earth. Now we are talking about here opaque solids which we see in our surroundings on the surface of the earth. If it is not opaque, then that radiation which is traveling in the space, if you have here opaque solid or transparent solid, how it behaves. If it is opaque solid, it is only the surface which is emitting or absorbing or reflecting. If it is not opaque, if it is transparent or semi-transparent, so whatever radiation is falling, but there is a source. It's not that radiation is existing there. There is some source of radiation. So some of it will be reflected, some of it will be absorbed, some of it will be transmitted. So the whole volume is taking part in this radiation transfer or radiation exchange. But here, in case of opaque solid, it's just a surface phenomenon. Okay. Because in opaque solid, it's only a few microns on the surface, which is taking part in that radiation heat transfer. Okay, now any surface, sun, this one, or any surface on the earth, which is producing radiation, which are a source of radiation. So we need to know how much radiation a surface is emitting. That is given by Stefan-Boltzmann law. So we know that if the temperature is higher than 0 Kelvin, it will emit radiation, but how much? Right? So that is given by this law. And this law simply written in this form. Actually, it is derived after doing all those integrations over all wavelengths, because radiation is emitted by these surfaces at different wavelengths. Higher wavelengths, smaller, medium, they are emitting in every direction at different wavelengths. So if you integrate over all wavelengths and in all directions, after doing those integrations, that is the final equation which we have here. And that is the maximum possible. Maximum possible radiation emitted, only emitted we are talking about, emitted by a body, not absorbed or transmitted. Emitted by a body is given by this equation. So here it depends upon, of course, again, surface area of that body, for that is the body. So it is emitting radiation because its temperature is greater than 0 Kelvin. So it depends upon its surface area. Again, this area, if it is emitting here, so this area will also be emitting radiation. This one, if it is placed in open space. So this whole area multiplied by temperature, but to the power 4. Okay, multiplied by that proportionality constant, which is called Stefan-Boltzmann constant. So the radiation emitted by any body, maximum possible. Maximum possible means all real bodies are actually emitting radiation less than this. Right? This is the maximum possible. Like in thermodynamics, we used to say that Carnot heat engine has the maximum possible efficiency at a given high and low temperature, TH and TL. That is the maximum possible. Similarly here, this equation is giving us maximum possible energy. That is energy, the units are energy, watts, Q dot. So A square, Kelvin to the power 4. Here you must use Kelvin. Never use Celsius here because it's not delta T anymore. So the units of sigma will be watts per meter square per Kelvin 4. It is the proportionality constant. And this is fixed value. It's not like H or K, that is fixed. Because that H and K were dependent upon in convection. We had HA delta T. For conduction, we have Ka dt by dx, where these proportionality constants depends upon the medium involved, material involved. Here it doesn't depend upon medium or material, so we have this one is a fixed constant. 5.6710 to the power minus 8 watts per meter square per Kelvin 4. Okay. This is called Stefan-Boltzmann constant. Its value in SI units and its value in English units.
So it's constant.
It's a constant. It's a fixed value, just like your universal gas constant, right? So it's a constant. Because it doesn't depend upon material medium in which the radiation is moving. Okay. So any body which obeys this equation is called black body. All real bodies will be emitting radiation less than this at a particular temperature and from that surface area. Okay. That is the maximum possible. That's why that ideal body which is emitting this radiation is called black body, or the radiation is called black body radiation. Okay. So if you know the area, if you know the temperature multiplied by sigma, we can find out the maximum possible radiation. So any body, so here is the maximum possible, it's 400 Kelvin temperature. So area is not written, so that's why this is what? Heat flux. So that's why units watts per meter. So from 1 meter square, this body can emit maximum this much radiation, 1452 watts per meter square. And the sun is very near to an ideal black body. Very near to ideal black body. So sun temperature is about 6000 Kelvin. In some books it is written as 5700, so something around this range, 5700 to 6000 Kelvin. So we can find out maximum possible being emitted by the sun is this much. So 5.6710 to the power minus 8 into, let's 6000 Kelvin to the power 4. So answer is this much watts from 1 meter square surface area of the sun. The outer surface area of the sun is emitting this much radiation, almost. Sun is one real thing which emits, which obeys this law. I don't know, more than 90% you can say. But all real surfaces here we see they emit less than this one. Which material gives near to this one, which we know? Black paint. Black paint. So here we have to add, if we use this term emissivity. So if I add here emissivity, for black body it is 1. Ideal black body. But for all real bodies, they will be emitting less than this. So for example, for black paint, this emissivity is 0.98. Black paint, normal black paint. Right.
And it depends only on the color.
No, not necessarily. It depends upon the composition of that material. That is emittance. Then we will learn another thing, absorptance. So black paint has this max, but there are other materials which are not black, artificially made substances which do not look like black, but they have very high emittance or absorptance.
And also skin is more than 90%.
Yeah, our human skin, it's not even black, even then its emission is more than 90%. Okay. So let's move on.
Do we use epsilon in the...
Yes, for real bodies, no. For real surfaces, equation should be written like this. The maximum possible radiation emitted by a real body at a particular temperature, but it's not just T to the power 4. So as the temperature increases, so you can see the effect, the amount of radiation emitted will increase significantly. Okay. Where E here we are defining as emissivity of the surface. So it means this emissivity will be between 0 and 1. It's a ratio. Actual divided by maximum possible. What is maximum possible? Sigma A Ts to the power 4. Okay. That is called emissivity. Actual radiation divided by radiation of a black body at that temperature. So here you see emissivity values for different substances. Like aluminium foil has very low emissivity if you compare it with, but water has very high emittance. Black paint. I saw human skin here also. 0.95. So when you have fever, only your temperature rises few degrees, only few degrees. Now our temperature is 98 degree Fahrenheit or 37 degrees Celsius. When it goes to 38 or 39, we feel very hot because e to the power 4. That's why heat emitted is so high. Okay. So all the bodies, they are not only emitting, they are also exposed to radiation from surrounding surfaces. The same body which is emitting, it is also receiving or intercepting radiation from the surrounding surfaces. So any body, there will be a radiation heat exchange with other bodies in its surroundings. Some of it is falling on it and it is also emitting. So there is continuously a net heat exchange going on between different bodies. Okay. So for example, sun is the major source of radiation, which is falling on different surfaces over the whole earth. So we can summarize it here. Any body, it is not only emitting radiation, it is also receiving radiation from the surroundings. So the radiation, so for that particular surface, we are using this symbol G for the radiation coming from the surrounding, and this symbol E for the radiation emitted by that body. And of course, if it is not vacuum, if there is some air or gas, so there will be a heat exchange by convection also. So both radiation and convection, both are taking place simultaneously. But radiation now has two parts, one leaving, one incident on the body, right? That is the more general case. And every surface has certain emissivity. This radiation emitted by that body is given by epsilon sigma Ts to the power 4. If I do not write area, it means per meter square, right? But the same body is also exposed to radiation. So now what this body will do with this one, if it is opaque, then some of it will be absorbed. So we use the term here absorption or absorptance or absorptivity of that body. So every body has emittance and it also has absorptance. So the black body, which is emitting this much, it is also absorbing this much. So a black body is not only a perfect emitter, it is also a perfect absorber. Whatever radiation will be falling on it, it will absorb all of it. But all real bodies, they will absorb less than a black body. So for that, we use the term alpha. So alpha, so how much will be absorbed here? Alpha into G. The rest either will be reflected or transmitted if it is transparent material. Okay. So now we have two terms, epsilon and alpha. Radiation emitted, radiation, amount of radiation absorbed with respect to black body. Amount of radiation emitted with respect to a black body, amount of radiation absorbed with respect to a black body. Right? So here we use the term irradiation. The radiation falling on the surface, we call it irradiation. And the radiation emitted by a body, we use the term either emissive power or simple radiation emitted. emitted radiation, and irradiation means radiation which is falling on the surface of a body. Okay, these are the two terms. So which is given by alpha. How much of this irradiation will be absorbed is given by this. Okay. So similarly, you can have another column of absorptance here for all these materials. And you will see all these materials do not have the same emittance and absorptance. So materials may have different emittance and different values of absorptance. For example, here black paint is one example here, which I know, which has same emittance and same absorptance, right? These copper, polished copper, look very low emittance. It also has very low absorptance. I do not know how much. That's why in all those solar-based applications where we are using those copper, we have to paint it black. If you do not paint it black, it's a poor absorber of solar radiation. So you do not use those metals without black paint in solar applications because they have very low absorptance compared to black paint. So you have to paint it black. They are good conductor, but not good absorber of radiation, and also poor emitter of radiation, right? Okay. So whenever we say copper is a best heat transfer material, it means it is only good conduction characteristics, not radiation, right? So this is explained here again. Whatever radiation is falling on a surface, a part of it will be reflected, a part of it will be absorbed, and a part of it will be transmitted. That absorbed part, what it will do? Increase the temperature because it is becoming energy, it is becoming internal energy of that body. So its temperature will rise, then it will start to radiate. As the temperature keeps on increasing, the amount of radiation emitted will also be increasing with T to the power 4. So these are two different things. Reflection and emission are two different phenomena. So this is normally a confusion. We normally treat reflection and emission as same. No. For example, this is a radiation coming from sun. Sun radiation are normally short wavelength radiation because here temperature is much higher. At much higher temperature, the radiation emitted by a surface is of high frequency. High frequency means low wavelength, small wavelength. But the radiation emitted by all these surrounding surfaces, their temperature is much less than sun temperature. So they emit radiation of longer wavelength. Small frequency and longer wavelength. If you remember that equation, H is equal to C lambda. E is equal to energy emitted. We will see in the radiation chapter. Vc over lambda. Energy of this radiation is given by frequency, speed of light divided by lambda. Okay, I think I wrote it correctly. Okay, anyways. So here I was telling you that reflection means the same radiation, the same short wavelength radiation is reflected. But emission means a part of it is absorbed, temperature is increased. Now this surface is emitting radiation, but that is of different wavelength than this one. This is emission, this is reflection, right? Transmitted also, it's the same thing. A part of it is transmitted. So now this body is, the radiation leaving from that body consists of reflection, emission, and transmitted part. So the sum of all these radiations leaving the surface in the form of emission, reflection, transmission, we use the term radiosity. The radiation leaving from any body, now it is leaving in the form of reflection, or in the form of emission, or in the form of transmitted. Transmitted is same as reflected, but it was not reflected. It went into the body and then left. If it is transparent, for opaque, this term will not be there. Only emission and reflection. If it is black body, only emission will be there. There will be no reflection. Only emission. Okay.
So what's radius?
Radiosity, the radiation. See this figure again. For example, this is a real surface on which radiation is coming from sun or from any other surface. A part of it is reflected, a part is absorbed, a part is transmitted. Now this body will also start to emit radiation. Now from this body, what type of radiation are coming from this body? Emission, reflection. So sum of all these is called radiosity.
Also the reflected.
Yes. So, total amount of radiation coming from a body consists of reflected part, transmitted part, and emitted part. Sum of all these is called radiosity.
The net of the radiation. Net of the radiation would be.
Yeah, the sum of all the radiation emitted by a body. Okay. So the part which is absorbed, so let me say this is G, a part of it is absorbed here. This is the absorbed part of this G. And this is the reflected part of this G. This is the transmitted part of this G. So this total G is equal to sum of it which is reflected plus sum of it which is absorbed plus sum of it which is transmitted. Right? So G divided by a common G, rho plus alpha plus transmittance, reflectance, absorptance, transmittance is 1. Okay. For a body. So that's how we define absorptance. All these are ratios. Fraction, which is reflected, fraction of the incoming radiation, which is absorbed, fraction of the incoming radiation, which is transmitted. For opaque solids, this will be 0. So it will be rho plus alpha is equal to 1 for opaque solids. For transparent or semi-transparent, all these three will be present. For a mirror, almost all of it is reflected. If 100% is reflected, then rho is equal to 1. But normally it's not. There is more than 90% is normally the reflection of a mirror. Okay. So we know what is black body. Black body is one which will absorb all of it. So a black body is a perfect absorber and also a perfect emitter. So all these points we have discussed, right? Let's move on. Now this absorptance, if we go further in more detail about radiation, absorptance of a material which we saw in that table, that also depends upon the type of radiation falling on a surface. For example, a body can absorb 90% of solar radiation, but it may not be absorbing 90% of any other type of radiation. Solar radiation is in a certain wavelength. So a body can have absorptance dependent upon the wavelength of radiation, right? So alpha depends upon the nature of irradiation as well as on the surface itself. So a surface can have different absorptance for different type of radiation falling on it, right? Absorptivity of a surface to solar radiation may differ from its absorptivity of radiation emitted by the walls of a furnace. Right? That surface, its absorptivity for sun could be different when it is inside a furnace. Now, this radiation versus this radiation, this alpha could be different for the same material. Right?
So we will have 2Q.
No, we will have different Qs in this case. Right? Either it will be exposed to sun or it will be exposed to furnace, inside a furnace. So a material may have different absorptance and different wavelengths.
So we have
Okay.
our formula is for one wave.
Yes, then yeah, that we'll see in radiation chapter. Then we will mention alpha with lambda. At that wavelength, this is the absorptance. At any other wavelength, absorptance could be different, right? That's why radiation becomes very complicated, and then we to simplify our mathematical models without losing too much accuracy, we do some assumptions. We'll see what we do in chapter 1. So this is the most common scenario. Like here you see a small surface is surrounded by a large surface. And we want to find out the radiation heat exchange between these two surfaces. This is a surrounding surface at temperature T surrounding. This is a small surface at temperature Ts. Now this surface is not only exposed to radiation. Exposed to radiation means irradiation on that surface, and it is also emitting radiation, E. Now, if the temperature of that surface is higher, Ts is greater than T surrounding, then the net radiation heat exchange will be from this to this. It is emitting more than absorbing. Or in other case, it could be G could be greater than E, or E could be greater than G. Both possibilities may exist. Now for this general case, we'll see a general equation with certain assumptions, which we can use in some practical problems. And look here, you have a gas. If it is separated by a gas like air, gases normally do not interfere with the radiation. They do not absorb, they do not reflect, they normally allow the radiation to pass through, right? So then the radiation heat exchange is only between these two surfaces. What air will be doing here?
Resistance.
Convection.
Convection. The heat transfer between this body and this body is by radiation, plus because there is air, it's by convection. Air is getting heated up and getting cooled down here. So air is also heat transfer carrier, but not in the form of radiation. In air, it is by convection. So the net radiation heat exchange for such a case, where two surfaces are involved and one surface is completely surrounding the other one. Now there are only two surfaces. In that case, the radiation heat exchange formula is this one. I'll give you the derivation in next slide. Before, what we said, Q dot radiation from a body, just one body, was epsilon sigma and its surface temperature. Now we are saying if there are two bodies involved and we want to find out radiation heat exchange between these two bodies, then it is Ts minus T surrounding to the power 4. Okay, so how it is derived? So let's see its derivation. I made a separate slide because I'm consuming more time here on the radiation basics, because I know from the previous semester, at the end of the semester, we left with so less time to cover radiation. That's why I'm trying to cover as much as possible in the first chapter. Okay. So it can be explained with the help of this, but I have another better explanation here. Now, here you see two bodies. One at temperature Ts, other at temperature T surrounding. right? This is body 1, this is body 2. The radiation emitted by body 1 at temperature Ts is given by this equation, which we just saw from Stefan Boltzmann law. But the other surrounding body is also emitting radiation. Surrounding body. How much? Epsilon of surrounding, sigma T of surrounding to the power 4 multiplied by area of surrounding. Okay. Now we want to find out how much is the net heat exchange between these two bodies. The radiation emitted by that body is this much, the radiation emitted by this body is this much. And this radiation emitted by the surrounding is also becomes irradiation for this one, right? So now here our body which is concerned to us is this one. We want to find out radiation heat exchange, radiation leaving, net radiation heat exchange from that body. So this will be falling on that body and a part of it will be absorbed. Here S I am using for this body, body 1 as surface, body 2 as surrounding. Okay. Now what will be the net radiation heat exchange? This minus this is what, which will be here. Okay. If I just see this body, this is my system.
So we neglect reflection. We neglect reflection.
Conduction,
Reflection.
reflection. Reflection is there, but look, reflection is already accounted here. When I say absorbed, the rest is reflected. So when I'm saying if this much is absorbed, so the rest is reflected. Okay, so this minus this or this minus this. It could be in under certain instances, this may be larger than this or this may be larger than this. So here I'm writing this emitted minus absorbed. What is absorbed? G into alpha. And what is G? This much. But this G, which is falling on that area, G is coming from this area of surrounding, but only the part which is falling on that area, surface area. So this equation is clear. This is leaving the surface. This is absorbed on this. Why absorbed? Because I'm multiplying with absorptance of that surface, S. But that is coming from surrounding. Surrounding temperature to the power 4. Surrounding emissivity. But area, not surrounding area. The area, this area over which it is falling or absorbed. This equation is clear. Now we can simplify this equation by using some assumptions. I'm assuming this surface is gray. Gray means any surface is called gray if its absorptance is equal to emittance, like black paint. If absorptance and emittance are nearly same, then it is called gray surface. So here I'm assuming gray surface, it means eta of S and alpha of S are same. So this will be common. Sigma is also common. Area is also common. So what is left? Ts to the power 4 minus T surrounding to the power 4. The equation which we saw. This is called radiation heat exchange. And also there is one more assumption. Where is eta of surrounding? This is assumed as 1, means I'm assuming this surrounding surface is a black body. That's why this is not here. This one is equal to this one. Absorptance is equal to emittance for that surface, because I'm saying it is a gray surface. Second major assumption, I'm assuming that surrounding body is a black body. That's why emittance of the surrounding body is 1. right? Like sun. If the surrounding surface is like sun, then I'm assuming eta of surrounding. So under these assumptions, this equation can be used to find out radiation heat exchange between two bodies. And one body is completely surrounding the other body. So this equation will be used to solve radiation problems in chapter 1. But we should know that there are certain assumptions. So one of the assumption is we are assuming gray surface. Second assumption that surrounding surface is black body.
So that's a good assumption.
Not a good assumption, but for some numerical problems, for example, this wall and surrounding sky can be solved using this equation. Surface is exposed to ambient sky. The other surface is sky. Air is not interfering with radiation. So for such cases, this is a good assumption. But for other cases where we cannot use this assumption, we have a much different equation where emissivity of both surfaces should be taken into account. Secondly, the orientation of objects is very important. Orientation means, look here, this equation which we wrote here, that is equation of radiation heat exchange from body 1 to body 2. This equation. What about 2 to 1? Will it be the same? This equation which we wrote, this is for 1 to 2. But can I write the same for 2 to 1?
Maybe yes.
Okay. Minus, that's all. The same equation, but you say it will be only the sign will change, could change. Look here, whatever radiation is leaving this surface, it is leaving in every direction. At every point, we can show that radiation is leaving in every direction like this. So whatever radiation is leaving from body 1 will reach body 2. So now apply the same here. The radiation leaving this body 2. So every part of this radiation will reach here or not? No, because this will never reach here. This will never reach here. Only this part, this portion will reach here. So here we need to add one more term here, depending upon the geometrical orientation of two bodies. And we call it view factor. F1 to 2 in this case is 1. All of the radiation leaving surface 1 will reach surface 2. So I can say F1 to 2 in this equation was 1. But F2 to 1 will not be 1, it will be less than 1. Maybe 70% of it will reach here, or 60% of it. So we need to add this view factor.
The surface area of the body 1.
Yeah. This is the surface area, only the top one we are talking about.
For body number 1.
For body number 1 and surface area of the body number 2.
We didn't take it into account. So
Yes, in this equation we are only saying that whatever radiation is leaving this surface from area AS will reach A2. But if you say the same thing for 2 to 1, the same surface area, but all of this radiation will not reach here.
yes, but we took the area of only of the surface.
Yes, only of the surface, but now you have to take the area of the second surface also. This ratio, area of 2 and area of 1, their orientation with each other, their area difference with each other, that must be taken into account if I want to write that equation from 2 to 1. For 2 to 1.
For 1 to 2, it's okay.
It's okay. For 2 to 1, it will be area A2. Yes, you're right. But now there will be another term, F2 to 1. So that makes things more complicated. So I have the derived form of that equation, that general equation in which these things are taken into account is this one. This is more accurate. This is from chapter 9 or 8 of radiation. I'm showing it in chapter 1 so that even if we are unable to cover it in the radiation part, so at least you know that we have this more general form to find out radiation heat exchange between two bodies. One is surrounding the other completely. Now you can see here both areas are taken into account. Emissivities of both are taken into account. We are not saying this is a black body. It has certain emissivity. And also this thing which I explained, it will not always be one. For example, let's see some more examples. Like this one, tube in tube. This is surface 1, this is surface 2. So what is F1 to 2? Whatever radiation will be leaving from that surface will reach surface 2. So F1 to 2 is 1. But F2 to 1 will be less than 1. Look, the radiation emitted by surface 2, a part of it will reach here, but this will not be reaching surface 1. So F2 to 1 will be less than 1. How less? So there is a complete topic of view factor in radiation chapter. So right?
Sir, but why it's important? Because we are only dealing about the surface, what's living in it, and what's
No, maybe we are interested in this surface also.
and
If this is our surface in concerned,
yes.
then I need to know F2 to 1.
Do we care what's reached the other surface?
Yes.
Like, we-
Look, some of it is falling over it again. So it is not reaching there. So if I say F2 to 1 is equal to 1, I am calculating higher Q which is leaving, but actually it is less. Some of it is falling over itself. So that should be taken. If I am interested in Q2 to 1, then,
I think so we are calculating.
okay,
No.
this is my surface 1, this is 2 now,
Yes.
okay?
No.
Now we are interested to know what is F1 to 2.
We're taking the sum of the radiation emitted
Mhm.
plus or minus the radiation
Coming
absorbed.
back itself,
Absorbed.
absorbed.
So we don't care about its reach to other surfaces.
Look, there are the two surfaces, there is radiation heat exchange going on, and I want to find out this Q dot radiation from 1 to 2. How to calculate it? Using this formula. This is the general formula to calculate radiation heat exchange between two surfaces. If one is completely surrounding the other, then we have to see if this F1 to 2 or F2 to 1 is 1 or less than 1. Right? This is what I want to calculate, heat transfer rate. That's what I'm interested in. Okay. So in chapter 1, we shall be using this equation. But this is more generalized one, right? More accurate one, right? But still there are certain assumptions. One of the major assumptions which is still present here is the directional dependence of radiation. Directional dependence means here we are assuming this surface is emitting radiation equally in all directions. But actually there is some direction. The real surfaces, they are not as smooth as we are showing them here, right? So they have some directional dependence, and they are emitting more in one particular direction and less in the other direction. That will also make more complicated. So here this assumption is still, that is called diffuse surface. One of the assumption was gray surface, which we used here. The second assumption, which is present in both of these, diffuse surface. Diffuse surface means it is emitting equally in all directions. Okay. Under these assumptions, these equations are valid, and those give you good results without losing too much of accuracy for normal flat surfaces. Okay. Okay, so I explained what is view factor, epsilon 1, epsilon 2 are emissivities. Okay, let's move on. So now let's come back to our governing equation of basic governing equation of radiation heat transfer, which we shall be using in this chapter, and that is given by this equation, Stefan-Boltzmann law. That is the radiation heat exchange between two surfaces. What are the assumptions? Gray, diffuse, I said diffuse, and also we are assuming this view factor from 1 to 2 is 1. And the surrounding body is black body. These 4 assumptions give you this equation, right? So between two bodies, now there are two bodies. Now we are interested to know the radiation heat exchange between two bodies. If this value comes out to be positive, it means radiation is heat transfer is taking place from this surface to this one. If it comes out to be negative, it means it is the direction is the other way around. Okay. And if there is air, okay. Now this radiation equation and the equation which we had for convection was HA delta T. For conduction, it was KA delta T by delta X. And now for radiation, epsilon sigma A Ts to the power 4 minus T surrounding to the power 4, two surfaces. These are the 3 basic equations which we learn in this chapter. If I want to write this equation simply in delta T form, like here, so we can do some mathematical manipulations here. I can write the same equation like this one or this one. I can write this equation like this. If I say K over delta X as H conductive A delta T, right? If I combine these. So this is H convective A delta T, that is H conductive A delta T. The same I want to write here, H radiative A delta T. So then what will be H radiative? Let me write it like this. Now what we can do here, epsilon, I want delta T here. So simple algebra. Can I write this one, T square minus T surrounding square into plus T surrounding square. This one like this. Okay. Further, epsilon sigma AS, I can write it as Ts minus T surrounding. That's what I want. What is left? Ts plus T surrounding and Ts square plus T surrounding square. This is my Q radiation, Q dot radiation. Now I want to write it as H A delta T. So here is A delta T. Whatever left is what? H radiation. So from here I can say H radiative or radiative heat transfer coefficient, convective heat transfer coefficient, conductive heat transfer coefficient. So radiative heat transfer coefficient is given by epsilon sigma Ts plus T surrounding into Ts plus T surrounding square. That is called radiative heat transfer coefficient, which is written here, Q radiation, HR A delta T, where HR is this, which I have. Okay. Any question?
Can you do it, please, to show us from 2 to 1? I mean, yes.
In this case, yes, from 2 to 1, the same thing you can write, T surrounding 4 minus T S4, same equation.
I mean,
Using this.
Can we divide it? The same way.
The same way, yes. Look, here now you have to assume this emissivity is 1. Only then you can write the same equation as T surrounding minus TS4. Yes, why not?
No, I meant when we divide it, the F12, I'm not.
Look, no, here we are neglecting F1 to 2.
No, I mean, if you wanted to.
Yes, then wait for radiation chapter. And that's a complete topic, view factor. Just see in your book, view factor. There are certain derivations for simple geometries, and for complex geometry, there are tables and very complex equations. Okay, so I'm telling you, this is the most complicated part of heat transfer. But unfortunately, in semester duration is so small, we have only 1 or 1.5 week at the end for radiation. That's why I'm covering at least the basics here. Okay. But now, in general, there will be air, then there will be both heat transfer by radiation from this surface to this plus convection. So there will be convection plus radiation part, both occurring simultaneously. But if I start from here, so from here to here is by conduction. Then there are 2.
So this is the third one.
Yeah. Now all simultaneous. That is the next topic. But before, we will solve a question. So this radiation heat transfer, if there is natural convection of air, generally, if it is natural convection of air, you cannot or you should not neglect radiative part. You should calculate H, Q radiative plus Q convective. But if it is forced convection, and if there is liquids involved, then this is definitely negligible compared to forced convection. Which you can, because the temperatures with which we are dealing is below around 100, 200 normally. We are not always solving sun. If there is sun, we cannot neglect radiation because the temperature is 6000 Kelvin. But for temperatures below 200 degrees Celsius, this radiation part is negligible compared to convective, forced convection. All right. So let's solve one numerical. That is written here. That for forced convection, radiation can be, but you need to check either it is negligible or not, because normally emissivities of those surfaces, metals, they have very low emittance, and when temperature is low, emittance is very low, then definitely radiation is negligible. In all these refrigeration, air conditioning applications, we neglect radiation. In all those heat exchangers which are used, not in boilers. Boilers, you have very high temperature, or furnaces. But for other applications, compared to forced convection, we neglect radiation part. So that's a good thing, good news. Otherwise, radiation is very complicated. Okay. So let's solve a numerical. Here there is a steam pipe. Again, heating. Heating of a room during winters. We are in Middle East. So heating of a room by steam flowing through a pipe. Okay. So now look what is data is given. In the surrounding air temperature is 25 and wall temperature, surrounding wall. Radiation always takes place between 2 solid surfaces. Gases normally do not interfere with radiation. So here air temperature, and you need to check if wall temperature is different from air or not. If different, then you need to use wall temperature for radiation heat exchange, not air temperature. Air temperature will be used for convection heat transfer. Okay. So now let's see what is given. An uninsulated steam pipe passes through a room in which the air and walls, both air and walls, clearly written, are at 25 degrees Celsius. The outside diameter of the pipe is 70 mm, and its surface temperature and emissivities, surface temperature and emissivity is given. What are the surface emissive power and irradiation? Surface emissive power, this is our surface, and irradiation means how much is falling over it, G. That's what we need to calculate. What are surface emissive power? If the coefficient associated with free convection, there is free convection of heat transfer. It means there is no fan, and that is also given. Is 15 watts per meter square per Kelvin. The units tells you exactly what it is. It is a coefficient, watts per meter square per Kelvin. What is the rate of heat loss from this surface per unit length of the pipe? Means for length of 1 meter. So first of all, we need to calculate surface emissive power E and irradiation G. Only E. It's not saying the net radiation heat exchange between these two bodies. Only leaving the surface. So we know what is E. Epsilon area T, yes, emissivity of the surface, area of the surface, Ts to the power 4. If area is not given, because here length is not given. So if area is not given, it's very simple. Assume 1 meter square, just like in thermo. If mass is not given, we assume 1 kilogram of mass. All right. So emissivity of the surface 0.8, 5.67 10 to the power minus 8 watts per meter square per Kelvin 4. Ts 200. This is very important. 200 plus 273. Okay, if you make this mistake now in this at this stage of your engineering, you will get significant marks will be deducted for this mistake. Okay, so you should know, you must know when to use Kelvin and when to use Celsius.
Can we use this small q instead of?
Yes, so write it as small e, emissive power, or Q dot radiative, or in this book, I think this is from others, not from Sengel, from the other book he is using Q double dot radiative. Okay. So the answer will be in watts per meter square because area is assumed. So this is emissive power of that surface. What is irradiation? G. How much is falling over it? Irradiation. What are the surface? Irradiation is coming from?
The walls.
From the walls. So G is actually coming from the wall. So sigma T of the wall. Area is not known. So 1 to the power 4. Emissivity of wall is given or not?
No, assume 1.
Assume 1. If wall, surrounding wall, emissivity is not given, so that is 1. So that is the irradiation on that surface coming from surrounding wall. Okay. Okay, just compare this room with this room. Here we do not have just walls in the surroundings. So for example, you want to find out radiation heat exchange between this surface and the surrounding. Now surrounding consists of wall made up of different material. This is, I think, wooden. This is different, but it is the paint which is emitting, because there is a surface of paint, so it will be emittance of this paint. This is different surface. This is different. So many surfaces. We are different. So now if you start calculating that radiation heat exchange, so there will be so many parts. Q radiation between 1 to 2, 2 to 2, 3 to 2, 4 to 2, 5 to 2, and so many view factors. So that becomes very complicated. But thanks God, compared to convection, because of the less emissivities, because of we are at very low temperatures, if there is forced convection, we can neglect.
But there's area here, as you have given the diameter.
Yes, area is given. So it's simply multiplied by that area.
Yeah.
So we are calculating everything for watts per meter square. So if area is known, so multiply by area. So these are very important terms: per unit area in heat transfer and per unit mass in thermodynamics. If actual mass or actual area is not given, you are calculating for a unit mass or a unit area. Okay. So solution is here. Simply go through the solution. Be careful about the units. Always remember Kelvin. Now we need to also calculate heat loss from that pipe to surroundings. Surrounding is not just wall, air also there. The second part is to calculate the heat loss from a unit length of the pipe. So how much is the heat loss? There are two types. There are two modes of heat transfer from the surfaces: convection and radiation. Dot. What is convection? H convective, which is given, which we will learn how to calculate convection chapters. Here it is given area. It's not saying per unit area, it's saying calculate per unit length of the pipe. So area is pi d L, which we can assume 1 here. So pi d we have to write now. Pi d into surface temperature minus ambient temperature. That is the convection part. The second radiative part is now between two bodies. Epsilon sigma area of the surface, which is again pi into d per unit length, multiplied by Ts to the power 4 minus T surrounding. T surrounding and T air can be different. Here in this question, those are same. Here it is Ts minus T air. Here is Ts minus T surrounding. Power 4. You can use Celsius here. You should not, must not use Celsius here. Okay. If this question is in English units, means here you can use Fahrenheit, and you must use here Rankine. So from here we can find out heat loss. So you can see here heat loss. This is by convection part. This is radiation part. Watts per meter per unit length of the pipe. Look here, it was natural convection. That's why those are comparable. Now just assume forced convection. Let's make it 500. So you will see this part will reach in thousands. If you make this convection coefficient from 15 to 500 for forced convection, for liquids it could be in thousands, for boiling condensation it could be up to lakh. So then this will be negligible in that case, and this reach in thousands. So you can simply check, just replace with 500, I think it will be around 20,000. So then this is negligible. Okay.
Next to the end of the surface of the pipe.
If it is a long pipe, fluid is entering here, leaving there. So what is that cross section means? Nothing. Okay. In that case. So this is radiation heat transfer under all those assumptions. Actual will be less than this one. So that's why in majority of the cases we neglect radiation compared to if there is convection, forced convection. This is radiation we are calculating more than actual. Actual is even less than this one.
Maximum.
Okay, so then we'll study simultaneous heat transfer.